Welcome. In this lecture in linear data analysis, which has multiple sessions, we'll explore how we can use data that don't appear to be linearly separable, but they do visually appear to be separable. The main concepts for this lecture are, what we'll do is we'll take our data and we'll embed them in a higher dimensional space. So a projection is where we go from a higher dimensional space to a lower dimensional space. Now we're going to reverse that process and we're going to consider embeddings. And we'll define a kernel function for the dot products of vectors that have been embedded. This will lead us to a very powerful concept that's called a gram matrix. As we go through this lecture, we can keep in mind a problem, which is how can we use data that are not linearly separable? Let's explore a simple two-dimensional example. Here we have data that are visually separable. We could imagine that, for example, a circle will separate these, and here the +1 class is indicated by cyan plus signs, and the -1 class is indicated by red circles. And we can see visually that these are not linearly separable, but they do seem to be separable. So what could we do? Well, now let's imagine that we take these two-dimensional data and we project them into 3 dimensions. What that means is we have to augment them. We have to add a dimension to the data. And the question is, how could we add this extra dimension? Well, one thing that we could do is we could append to each one of these observations the squared norm of the observation. And what we can see is that in 3D, the data become linearly separable by a plane, and that plane projects to a horizontal line in 2 dimensions. A more systematic way we can do it is referred to as a quadratic embedding. And in this quadratic embedding, it's not visually appealing the way that the other one was, but here we can see that there's a 2-dimensional line that separates our +1 data from our -1 data, and so that means in 3 dimensions, there's a plane that separates our data. Now, we're going to be discussing observations in this lecture, and we'll introduce a new notation. So each observation is a row, and what we'll do is we'll write the row, so we'll write the ith observation or the ith row using an underscore. This is an unusual notation, but we'll find it really useful and powerful. We'll also introduce a useful fiction, and that is we'll define a dot product. Now we understand that for an observation, each one of the variables will typically have a different physical meaning, and so we can't really square things and add them. But a useful fiction in linear data analysis is we'll define a dot product. You could think of a dot product in terms of a summation, or you can think of it vectorially. And either way, what we'll do for this lecture and a few subsequent lectures is we'll treat a row as though it's a vector in a vector space. We'll write it using an underscore, but it has all real entries and there are n of them, and when we've defined a dot product, we're going to treat a row as though it's a vector.